on projectile motion. In this presentation, I'll walk you through my experiment, my models, and how well the models compare to the actual data. In this lab, I wanted to test how well simplified physics models, first without drag and then with drag, predict a real projectile trajectory. By comparing the models with experimental data, I was able to see which assumptions would hold and where deviations would occur. This slide basically just recaps the main physics we use. The net force gives acceleration. Gravity always acts downward. Drag opposes motion and it scales with speed squared. The projectile motion is in the combination of the horizontal and vertical components under these forces. Okay, so to collect experimental data, I recorded the ball's motion in a fixed camera view so the motion was planar. I fixed a calibration stick so the distances in the video could be converted to real units. And a tracker had a fine axis so that X is horizontal and the origin is directly under the release point. I also measured the ball's mass and the height from which it was thrown. Okay, tracker data. This is a screenshot of the tracker setup that I had. It shows the coordinate axes, the path, and the calibration stick. Below or to the side is a table of sample data, times and corresponding X and Y positions extracted from the video. I use this data as an experimental baseline to compare with my computational models. Okay, so this is my first model. It was gravity only. In this model I turned off drag, so setting B equal to 0, and the only force is gravity. The trajectory is the ideal parabolic curve predicted by classical projectile motion, meaning no air resistance because no horizontal force acts. Horizontal velocity is constant and then vertical motion is symmetric about the peak. Okay, in this version I included drag. Drag force always opposes motion and scales with speed squared. As a result, the projectile doesn't travel as far horizontally. The ascending portion is slowed and the descent is steeper. This model is more realistic for real world projectiles, so more like what would actually probably happen if this were done. Okay, model versus experiment. This is the key comparison. The black dots represent the experimental tracker path. The dashed curve is the gravity only model, and the solid curve is gravity plus drag. You can see which model tracks the real data more closely, and kind of see what the difference is between these. System and surroundings. When modeling, the system is just the projectile. The surroundings provide forces, gravity from Earth and drag from air medium. We neglect other forces, like wind, spin, buoyancy, just to make it a little simpler. So it's only gravity and drag, basically. And we have the projectile, which is the paper ball, surroundings with the Earth, and the forces considered, which are gravity and drag. Okay. Initial conditions. These are the initial conditions I input into the model. The initial position comes from tracker data. Initial velocity was estimated from the video, and the mass is measured or assumed. The drag constant was tuned to best match the data, and these values feed into the computational models. In the gravity-only model, velocity increases in the magnitude without bound until the projectile lands. There's no terminal velocity. But in the drag-included model, as speed increases, drag grows until it balances gravity, giving zero net acceleration, that is terminal velocity. Though our experiment may not reach that regimen because of short time, the model predicts it. If not reached, the terminal velocity curve is asymptotic. I could design another experiment to observe terminal velocity directly if I wanted to see it. What if I threw this object straight upward with the same speed, the time of flight would be longer than the angled throw? That's because the object is going all the way up, so it's going to its apex and then coming down. So the total time is TV0 divided by g. So in the angled throw, it's not going up as much, so the vertical drag time is shorter. Errors and uncertainties. Potential sources of error. The video calibration is probably not perfect. The frame rate also limits, what we can see. The drag constant is assumed, whereas real drag, we would know it and figure out based on things like spin and wind, which we ignored, and the numerical method may accumulate error. So all of these contribute. In conclusion, from the overlay comparisons, it is clear that including drag improves the match to real data.